What if the first humans to leave our galaxy are already alive today? Imagine a future where the stars are no longer distant points of light, but destinations within our reach. The idea of intergalactic travel, journeying beyond the Milky Way to explore other galaxies, sounds like science fiction. But what if it's closer to reality than we think? In this video, we'll dive into 30 groundbreaking theories about how humanity might one day achieve the impossible, the first intergalactic voyage. From wormholes that bend the fabric of spacetime to ships that carry generations of travelers across the cosmos, these theories push the boundaries of what we know and challenge us to dream bigger. So, are you ready to explore the mysteries of the universe and uncover the possibilities that lie beyond our galaxy? Stay with us, because by the end of this video, you'll see the cosmos in a whole new light. Let's begin. Now, let's step into the realm of one of the most fascinating ideas in theoretical physics, wormholes. Picture this: a tunnel carved through the very fabric of spacetime, connecting two distant points in the universe. These cosmic shortcuts, often called Einstein-Rosen bridges, could theoretically allow us to travel between galaxies in the blink of an eye, bypassing the vast distances that would otherwise take millions or even billions of years to cross. Imagine stepping into one end of a wormhole near Earth and emerging near a star system in another galaxy, all within moments. It's a concept that feels straight out of a science fiction novel, but it's rooted in the equations of general relativity. The idea hinges on the bending of space-time, a phenomenon predicted by Einstein's theory. Wormholes would require immense amounts of energy to create and stabilize, and here's where things get tricky. Theoretically, they could exist, but keeping them open long enough for anything or anyone to pass through is a monumental challenge. The problem lies in their instability. Without some form of exotic matter or negative energy to hold them open, wormholes would collapse almost instantly. And even if we could stabilize them, navigating through one would be fraught with risks, from intense gravitational forces to the possibility of the wormhole collapsing mid-journey. Despite these hurdles, the potential of wormholes is staggering. They could revolutionize our understanding of space travel, offering a way to traverse the cosmos without the limitations of speed or time. But for now, they remain a tantalizing possibility, a glimpse into what might one day be possible if we can unlock the secrets of spacetime itself. So, while wormholes may not be ready for intergalactic travel just yet, they remind us that the universe is full of mysteries waiting to be solved, and perhaps one day conquered. Now, let's shift our gaze to another groundbreaking concept that could redefine the way we think about space travel: the Alcubierre Warp Drive. Imagine a spacecraft not moving through space, but rather bending the fabric of spacetime itself to bring distant stars closer. This isn't science fiction, it's a theoretical idea proposed by physicist Miguel Alcubierre in the 1990s, and it offers a tantalizing possibility for faster-than-light travel without breaking Einstein's laws of relativity. Here's how it works. Instead of trying to propel a ship through space at impossible speeds, the Alcubierre drive would create a warp bubble around the spacecraft. Inside this bubble, spacetime would contract in front of the ship and expand behind it, effectively allowing the ship to ride a wave of distorted spacetime. To put it simply, the ship itself wouldn't be moving faster than light. It would be the space around it that's doing the work. This clever loophole means that, in theory, the ship could travel vast distances in a fraction of the time it would normally take, all without violating the cosmic speed limit set by the speed of light. But, as with all revolutionary ideas, there's a catch. The Alcubierre drive requires an enormous amount of energy that we currently have no way of generating. Some estimates suggest it would need the equivalent of the mass energy of an entire planet, or even a star, to create the necessary warp bubble. And then there's the issue of exotic matter, a hypothetical substance with negative energy density, which would be needed to stabilize the bubble and prevent it from collapsing. While exotic matter hasn't been discovered yet, its existence is allowed by certain equations in quantum physics, keeping the dream of the Alcubierre drive alive. Despite these challenges, the concept has sparked a wave of excitement and research. Scientists are exploring ways to reduce the energy requirements, and some even suggest that advanced civilizations might already be using similar technology. The Alcubierre drive reminds us that the universe is full of possibilities, and while we may not have the answers yet, the pursuit of such ideas pushes the boundaries of what we believe is possible. So, while warp drives might still be a distant dream, they represent a bold step toward a future where the stars are no longer out of reach. Now, let's turn our attention to a concept that feels almost like a story from a science fiction novel, but one that scientists have seriously considered: generation ships. Picture this: a massive spacecraft carrying not just a crew, but an entire community of people, embarking on a journey so long that multiple generations will live and die before reaching their destination. This is the idea behind generation ships, a potential solution for intergalactic travel when faster-than-light technology remains out of reach. The concept is both fascinating and daunting. A generation ship would essentially function as a self-sustaining ecosystem designed to support human life for centuries or even millennia. The original crew would board the ship knowing they would never see the destination. Their children, grandchildren, and great-grandchildren would be the ones to eventually arrive at a new galaxy, carrying the legacy of their ancestors. It's a profound thought, a mission that spans lifetimes, requiring not just technological innovation, but a complete rethinking of how we approach space travel. But with such an ambitious idea comes significant challenges. First, there's the issue of logistics. How do you design a ship that can sustain life for hundreds or thousands of years? It would need to produce food, recycle water and air, and maintain all systems without fail. Even the smallest malfunction could spell disaster for an entire generation. And then there's the question of population control. How do you ensure that the ship's population remains stable over such a long period? Too many people and resources could run out. Too few, and the mission could fail due to a lack of skilled individuals to maintain the ship. Beyond the technical hurdles, there are deep ethical questions to consider. Is it fair to ask people to live their entire lives aboard a ship, knowing they'll never see Earth or the destination? What about the psychological impact of living in such a confined, isolated environment for generations? And how do you preserve the cultural and social identity of the crew over such a long journey? These are questions that don't have easy answers, but they're essential to address if generation ships are ever to become a reality. Despite these challenges, the idea of generation ships captures the imagination. They represent a bold vision of humanity's resilience and determination to explore the cosmos, no matter how long it takes. While the concept may seem far-fetched today, it reminds us that the journey to the stars might not be a sprint but a marathon, one that could span generations. And who knows, perhaps one day, a ship carrying the descendants of its original crew will arrive in a distant galaxy, fulfilling a dream that began centuries before. Now, let's shift our focus to a concept that feels like it's straight out of a futuristic movie: cryogenic suspension. Imagine a scenario where humans are placed in a deep, frozen sleep, preserved for centuries as their spacecraft travels across the vast expanse of space. This is the idea behind cryogenic suspension, a potential solution for intergalactic travel that could allow us to bypass the limitations of human lifespans. The concept is simple yet revolutionary. Instead of spending generations aboard a ship, travelers would be placed in a state of suspended animation, effectively pausing their biological processes until they reach their destination. This would eliminate the need for generation ships and their associated challenges, such as maintaining a stable population or ensuring the mental well-being of a crew over centuries. Cryogenic suspension could make intergalactic travel more efficient, allowing humans to sleep through the journey and wake up in a new galaxy ready to explore. But as with any groundbreaking idea, there are significant scientific hurdles to overcome. First, there's the challenge of safely freezing and reviving a human body. While cryopreservation has been successfully used for small tissues and cells, scaling it up to an entire human is a monumental task. The process would need to prevent ice crystals from forming and damaging cells, a problem that has yet to be fully solved. Additionally, the technology to revive someone from such a state without causing harm is still in its infancy. Scientists are exploring methods like vitrification, which uses special chemicals to turn tissues into a glass-like state, but even this approach is far from being ready for human use. Beyond the technical challenges, cryogenic suspension raises profound ethical questions. What happens if something goes wrong during the freezing or revival process? Could there be long-term effects on the human body or mind that we don't yet understand? And what about the psychological impact of waking up in a completely different era, potentially centuries or even millennia after you were last conscious? These are questions that don't have easy answers, but they're crucial to consider if cryogenic suspension is ever to become a viable option for space travel. Despite these challenges, the idea of cryogenic suspension holds immense promise. It represents a bold step forward in our quest to explore the cosmos, offering a way to overcome the limitations of human biology. While the technology is still in its early stages, it's a reminder that the future of space travel might not just be about building faster ships, but also about reimagining how we experience time itself. And who knows, perhaps one day the first humans to reach another galaxy will do so not as a crew, but as travelers waking from a long, frozen sleep, ready to step into a new world. Now let's turn our attention to a concept that feels like it's straight out of science fiction, yet holds a surprising amount of scientific merit: self-replicating probes. Imagine tiny, intelligent machines capable of not only exploring distant galaxies, but also building copies of themselves along the way. These probes could act as the ultimate pioneers, venturing into the unknown and preparing the way for human explorers to follow. The idea is both simple and ingenious. A self-replicating probe would be equipped with advanced artificial intelligence and the ability to harvest raw materials from asteroids, planets, or even moons. Using these resources, it could construct new versions of itself, which would then continue the journey, spreading out across the galaxy like a cosmic network. This approach would allow us to explore vast regions of space without the need for human presence, at least initially. It's a way to extend our reach far beyond what we could achieve with manned missions alone. From a technological standpoint, the challenges are immense but not insurmountable. The probes would need to be incredibly durable, capable of surviving the harsh conditions of space for centuries or even millennia. They would also require sophisticated programming to make decisions autonomously, from selecting the best materials for replication to navigating through uncharted regions of the cosmos. Advances in robotics, artificial intelligence, and materials science are bringing us closer to making this a reality, but there's still a long way to go. Beyond the technical hurdles, self-replicating probes raise fascinating philosophical questions. If these machines are capable of independent thought and decision-making, do they possess a form of consciousness? And if they're creating copies of themselves, who or what is truly in control of their mission? These questions touch on the nature of intelligence, autonomy, and even the definition of life itself. They challenge us to think deeply about our role as creators and the ethical responsibilities that come with it. There's also the question of what happens if these probes encounter extraterrestrial life. How would they interact with alien civilizations, and what protocols would they follow? The idea of self-replicating probes spreading across the galaxy brings with it the potential for both incredible discovery and unforeseen consequences. It's a reminder that our exploration of the cosmos isn't just about technology, it's also about the values and principles we carry with us. Despite these challenges, the concept of self-replicating probes offers a tantalizing glimpse into the future of space exploration. They could serve as our eyes and hands in the universe, mapping out new worlds and preparing the way for humanity's eventual arrival. It's a vision that combines the best of our ingenuity and ambition, pushing the boundaries of what we thought was possible. And who knows, perhaps one day the first signs of life in another galaxy won't be from aliens, but from our own self-replicating probes, quietly building a bridge between the stars. Now, let's venture into one of the most daring and mind-bending theories of intergalactic travel: black hole slingshots. Picture this: a spacecraft harnessing the immense gravitational pull of a black hole to catapult itself across the cosmos at speeds that defy imagination. It's a concept that sounds like it belongs in a blockbuster sci-fi movie, but believe it or not, it's grounded in real physics. The idea revolves around something called a gravitational slingshot, a maneuver already used in space exploration, though on a much smaller scale. For example, NASA has used the gravity of planets like Jupiter to give spacecraft a speed boost, but with black holes, the stakes and the potential are exponentially higher. Black holes possess such intense gravity that they can bend spacetime itself, creating an opportunity to accelerate a spacecraft to a significant fraction of the speed of light. Theoretically, this could cut down travel time between galaxies from millions of years to something far more manageable. Here's how it might work. A spacecraft would approach a black hole at just the right angle, using its gravity to swing around it like a cosmic slingshot. The black hole's immense pull would fling the spacecraft outward at incredible speeds, much like a stone launched from a sling. But unlike a simple planetary slingshot, the energy gained from a black hole could be enough to propel the craft across vast intergalactic distances. However, this isn't without its risks. Black holes are among the most dangerous objects in the universe. Get too close, and the spacecraft could be torn apart by tidal forces, the difference in gravity between the side of the craft nearest to the black hole and the side farthest away. Even if the craft survives, navigating the extreme gravitational environment requires pinpoint precision. A miscalculation could send the spacecraft spiraling into the black hole's event horizon, where not even light can escape. The physics behind this theory is both fascinating and complex. It relies on Einstein's theory of general relativity, which describes how massive objects like black holes warp spacetime. By carefully plotting a trajectory that skirts the edge of a black hole's gravitational influence, a spacecraft could theoretically exploit this warping to gain enormous speed. But doing so would require an unprecedented level of technological sophistication, from advanced propulsion systems to real-time navigation algorithms capable of adjusting to the black hole's chaotic environment. Beyond the technical challenges, there's also the question of finding the right black hole. Not all black holes are created equal. Some are too small, others too large, and many are simply too far away to be practical. Identifying a suitable candidate would be a monumental task in itself, requiring detailed astronomical surveys and perhaps even interstellar probes to scout ahead. Despite these hurdles, the idea of using black holes as cosmic slingshots is a tantalizing one. It represents a bold fusion of cutting-edge physics and audacious engineering, pushing the boundaries of what we think is possible. And while it may sound like science fiction today, who's to say what the future holds? After all, the history of space exploration is filled with ideas that once seemed impossible until they weren't. So, as we ponder the potential of black hole slingshots, we're reminded once again of the incredible ingenuity and ambition that drive humanity's quest to explore the cosmos. It's a journey filled with challenges, but also with limitless possibilities. And who knows, perhaps one day, black holes won't just be objects of fear and mystery, they'll be the gateways to the stars. Now, let's shift our focus to a theory that could revolutionize not just how we travel between galaxies, but how we stay connected across the vastness of space: quantum entanglement communication. Imagine being able to send messages instantaneously, no matter how far apart 2 points are in the universe. It sounds like magic, but it's rooted in the strange and fascinating world of quantum physics. Quantum entanglement is a phenomenon where 2 particles become linked in such a way that the state of one instantly influences the state of the other, no matter the distance between them. This connection defies our everyday understanding of space and time, as it seems to bypass the speed of light, which Einstein's theory of relativity tells us is the universe's ultimate speed limit. For intergalactic travel, this could be a game changer. If we could harness quantum entanglement for communication, it would mean that astronauts traveling to another galaxy could stay in real-time contact with Earth, eliminating the delays that currently make interstellar communication impractical. Here's how it might work. Pairs of entangled particles would be created and separated, with one set remaining on Earth and the other traveling aboard the spacecraft. By manipulating the state of the particles on Earth, we could instantly transmit information to the particles on the spacecraft and vice versa. This would allow for instantaneous communication, making it possible to send instructions, receive updates, or even share discoveries in real time, no matter how far the spacecraft has traveled. But as groundbreaking as this sounds, there are significant challenges to overcome. For one, creating and maintaining entangled particles over such vast distances is no small feat. Quantum states are incredibly fragile and can be easily disrupted by external forces, a problem known as decoherence. Additionally, while entanglement allows for instantaneous correlation between particles, it doesn't allow for the direct transmission of information in the way we typically think of communication. Instead, it requires a classical communication channel to interpret the results, which still faces the limitations of the speed of light. Despite these hurdles, the potential applications are staggering. Beyond intergalactic travel, quantum entanglement communication could transform fields like cryptography, computing, and even our understanding of the universe itself. It's a reminder that the laws of quantum mechanics, while strange and counterintuitive, hold the keys to unlocking technologies that could reshape our future. As we explore this theory, we're reminded of the incredible possibilities that lie at the intersection of science and imagination. Quantum entanglement communication may still be in its infancy, but it represents a bold step toward a future where the vast distances of space no longer isolate us. Instead, they become bridges connecting humanity across the stars in ways we're only beginning to imagine. And who knows, perhaps one day, the mysteries of quantum physics will make the impossible possible, bringing us closer to the dream of intergalactic exploration. Now, let's turn our attention to a concept that could redefine how we think about energy in the cosmos: Dyson Spheres. Imagine a structure so vast and ambitious that it could capture the entire energy output of a star. This isn't science fiction, it's a theoretical megastructure that could one day power humanity's journey to other galaxies. A Dyson sphere is essentially a massive shell or swarm of orbiting structures built around a star to collect its energy. The idea, first proposed by physicist Freeman Dyson, suggests that an advanced civilization could construct such a system to meet its enormous energy needs. For intergalactic travel, this could be a game changer. The energy required to propel spacecraft across the unimaginable distances between galaxies is staggering, and a Dyson sphere could provide the solution by harnessing the power of an entire star. Here's how it might work. The sphere, or a swarm of smaller structures, would capture the star's light and heat, converting it into usable energy. This energy could then be stored, transmitted, or used directly to power spacecraft, potentially enabling journeys that would otherwise be impossible. The scale of such a project is almost beyond comprehension. building a Dyson Sphere would require materials and engineering capabilities far beyond anything we currently possess. It would involve dismantling planets, asteroids, and moons to gather the necessary resources, and constructing a structure that could withstand the immense forces and temperatures near a star. But the challenges don't stop there. Maintaining a Dyson Sphere would require advanced automation and robotics to handle repairs and adjustments, as human intervention would be impractical at such scales. There's also the question of how to transmit the harvested energy across vast distances without significant loss. Some theories suggest using directed energy beams or other advanced technologies, but these remain speculative. Despite these hurdles, the potential benefits are immense. A Dyson Sphere could provide virtually limitless energy, not just for intergalactic travel but for sustaining entire civilizations. It could also serve as a stepping stone for even more ambitious projects, such as moving stars or creating artificial habitats on a cosmic scale. As we consider the possibilities, it's clear that the concept of a Dyson Sphere pushes the boundaries of what we believe is possible. It challenges us to think bigger, to imagine a future where humanity's reach extends far beyond our solar system. While the engineering and logistical challenges are daunting, they remind us that the greatest achievements often begin as bold ideas. And who knows, perhaps one day the energy of a star will light the way to the stars beyond. Now, let's shift our focus to a technology that could revolutionize the way we navigate the cosmos: artificial intelligence pilots. Imagine a spacecraft capable of making split-second decisions, adapting to unforeseen challenges, and charting the safest course through the vast emptiness of intergalactic space. This isn't just a futuristic dream, it's a necessity for humanity's journey beyond our galaxy. Artificial intelligence, or AI, could play a critical role in piloting spacecraft across unimaginable distances. Unlike human pilots, AI systems wouldn't be limited by biological constraints like fatigue, reaction time, or the need for life support. They could operate continuously, analyzing vast amounts of data in real time to make decisions that ensure the safety and success of the mission. One of the biggest challenges of intergalactic travel is the sheer unpredictability of space. From navigating through asteroid fields to avoiding cosmic radiation, the journey is fraught with dangers that require constant vigilance. An AI pilot could monitor every aspect of the spacecraft's environment, adjusting course, speed, and systems to avoid hazards and optimize efficiency. It could also predict potential issues before they arise, using advanced algorithms to simulate scenarios and develop solutions in advance. But the role of AI goes beyond just navigation. It could also manage the spacecraft's life support systems, ensuring that everything from oxygen levels to temperature remains stable for the crew, or even for cryogenically frozen passengers. In missions where humans are absent, AI could take full control, making decisions about when to explore, when to collect data, and when to move on to the next destination. This level of autonomy would be essential for missions to distant galaxies, where communication delays with Earth could take thousands or even millions of years. Of course, developing such advanced AI systems comes with its own set of challenges. We'd need to create algorithms that are not only highly intelligent but also capable of ethical decision-making. For example, how would an AI prioritize the safety of the crew versus the success of the mission? How would it handle situations where there's no clear right or wrong answer? These are questions that scientists and ethicists are already grappling with as we move closer to integrating AI into space exploration. Despite these challenges, the potential of AI pilots is immense. They could enable missions that are too risky or complex for human crews, opening up new frontiers in our exploration of the universe. And as AI technology continues to advance, the possibilities are only going to grow. From piloting spacecraft to managing entire colonies on distant planets, AI could become the backbone of humanity's intergalactic future. As we look ahead, it's clear that artificial intelligence will be a key player in our quest to explore the cosmos. It's not just about building faster or stronger spacecraft, it's about creating systems that can think, adapt, and thrive in the face of the unknown. And with AI at the helm, the stars may be closer than we think. Now, let's venture into a concept that stretches the boundaries of our imagination: multiverse pathways. What if the key to intergalactic travel lies not just within our universe, but in the very fabric of alternate realities? This idea, rooted in multiverse theories, suggests that the cosmos might be far more complex and interconnected than we've ever imagined. The multiverse theory proposes that our universe is just one of countless others, each with its own unique set of physical laws and dimensions. Some scientists speculate that these alternate universes could exist parallel to our own, separated by thin membranes or hidden pathways. If such pathways exist, they might offer a shortcut for intergalactic travel, allowing us to bypass the vast distances of our own universe entirely. Imagine a spacecraft equipped with technology capable of detecting and accessing these hidden pathways. Instead of traveling through the emptiness of space, it could slip into another dimension, traverse a short distance, and re-emerge in a galaxy millions of light years away. This would revolutionize our understanding of space travel, turning what once seemed impossible into a tangible possibility. But how would we even begin to explore such a concept? One approach involves the study of quantum mechanics, where particles can exist in multiple states simultaneously. Some theories suggest that these quantum phenomena might hint at the existence of parallel universes. If we could harness this knowledge, we might develop tools to manipulate spacetime itself, creating portals or bridges between dimensions. Of course, the challenges are immense. Navigating through alternate universes would require technology far beyond our current capabilities. We'd need to understand the fundamental differences between these dimensions, such as variations in gravity, time, or even the nature of matter itself. And then there's the question of safety. What happens if a spacecraft becomes trapped in another universe, unable to return? Despite these hurdles, the idea of multiverse pathways is incredibly compelling. It opens up a realm of possibilities that go beyond the limits of our own universe. Could there be civilizations in these alternate dimensions already traveling between galaxies with ease? Could we one day join them, exploring not just our universe, but the infinite tapestry of realities that might exist alongside it? As we ponder these questions, one thing becomes clear: the multiverse theory challenges us to think bigger. It reminds us that the universe or universes are far stranger and more wondrous than we've ever imagined. And if we can unlock the secrets of these pathways, the stars may not be the limit after all. Now, let's shift our focus to a concept that sounds like it's straight out of science fiction, but is grounded in real science: light sail propulsion. Imagine a spacecraft that doesn't rely on traditional fuel, but instead harnesses the power of light itself to journey across the cosmos. This is the fascinating idea behind light sails, a technology that could one day propel us to the stars. Light sails work by using the pressure of light, yes, light, to push a spacecraft forward. Here's how it works. A large, ultra-thin sail, often made of reflective material like mylar, is attached to a spacecraft. When powerful lasers on Earth or in orbit beam intense light onto the sail, the photons in that light exert a tiny but constant force. Over time, this force can accelerate the spacecraft to incredible speeds, potentially reaching a significant fraction of the speed of light. The beauty of this method lies in its simplicity and efficiency. Unlike traditional rockets that require massive amounts of fuel, light sails rely on an external energy source, lasers, to provide the thrust. This means the spacecraft itself can be much lighter, allowing it to accelerate faster and travel farther. In theory, a light sail-powered spacecraft could reach speeds that would make intergalactic travel feasible, even if it would still take thousands or even millions of years to reach distant galaxies. But how practical is this idea? Scientists have already tested small-scale versions of light sails, such as the Breakthrough Starshot project, which aims to send tiny probes to our nearest star system, Alpha Centauri, using this technology. While these early experiments are promising, scaling up light sails for human intergalactic travel presents significant challenges. For one, the lasers required to propel a larger spacecraft would need to be unimaginably powerful, far beyond anything we can currently build. Additionally, maintaining the precision needed to keep the laser beam focused on the sail over such vast distances would be a monumental task. Another consideration is the time factor. Even at a fraction of the speed of light, traveling to another galaxy would take an incredibly long time, far longer than a human lifetime. This raises questions about the purpose of such missions. Would we send robotic probes to explore and send back data? Or could we find ways to sustain human life on these journeys, perhaps through advanced hibernation or generation ships? Despite these challenges, light sail propulsion represents a bold and innovative approach to space travel. It challenges us to think beyond the limitations of traditional propulsion methods and explore the potential of harnessing natural forces like light. Who knows, one day we might look up at the stars and see not just distant points of light, but the glimmer of sails catching the beams of powerful lasers, carrying humanity's dreams to the farthest reaches of the universe. As we consider the possibilities of light sails, we're reminded once again that the future of space travel is limited only by our imagination and our willingness to push the boundaries of what's possible. Now, let's take a step into the realm of one of the most mind-bending concepts in physics, time dilation. Imagine boarding a spacecraft capable of traveling at a significant fraction of the speed of light. As you accelerate closer to this cosmic speed limit, something extraordinary happens. Time itself begins to warp. This phenomenon, predicted by Einstein's theory of relativity, could fundamentally alter how we experience intergalactic travel. Here's how it works. According to Einstein's theory, time isn't constant. It flows differently depending on how fast you're moving relative to something else. For a spacecraft traveling near the speed of light, time would pass more slowly for the travelers on board compared to those left behind on Earth. This means that while thousands or even millions of years might pass on Earth during an intergalactic journey, the travelers themselves might experience only a fraction of that time. To them, the trip could feel like mere decades or centuries, depending on how close they get to the speed of light. This concept, known as time dilation, has been experimentally confirmed in smaller scales. For example, atomic clocks on fast-moving airplanes or satellites tick slightly slower than those on the ground. But when applied to intergalactic travel, the implications are staggering. A journey to a galaxy millions of light-years away might seem impossible due to the sheer time span involved. Yet, for the travelers, the trip could feel manageable, even if it spans generations for those on Earth. However, this raises intriguing questions. If time dilation allows travelers to experience shorter journeys, what happens to the world they leave behind? By the time they return, if they ever do, Earth and its civilizations might be unrecognizable, having evolved or even vanished over the eons. This creates a profound ethical and emotional dilemma. Would humanity be willing to send explorers on missions where they might never see their home again, even if the journey feels shorter for them? There's also the challenge of reaching such incredible speeds. To achieve time dilation effects significant enough to make a difference, a spacecraft would need to travel at a substantial fraction of the speed of light. This would require propulsion systems far beyond our current capabilities, such as antimatter engines or warp drives. Even then, the energy requirements and technological hurdles would be immense. Yet, the idea of relativistic travel offers a tantalizing glimpse into the future of space exploration. It suggests that the vast distances between galaxies might not be as insurmountable as they seem, at least from the perspective of the travelers. Time dilation could turn what appears to be an impossible journey into a feasible one, at least in terms of the subjective experience of those on board. As we ponder the possibilities of relativistic travel, we're reminded that the universe operates by rules that often defy our everyday intuition. Time dilation challenges our understanding of reality, showing us that time itself is not an absolute but a flexible dimension shaped by motion and gravity. It's a concept that not only reshapes our approach to intergalactic travel, but also deepens our appreciation for the strange and wondrous nature of the cosmos. With this in mind, let's turn our attention to another groundbreaking idea: the role of exotic matter and negative energy in enabling intergalactic travel. Could these mysterious substances hold the key to unlocking the secrets of faster-than-light travel? Let's explore that next. Now, let's venture into the realm of the truly extraordinary, exotic matter and negative energy. These concepts might sound like they belong in the pages of a science fiction novel, but they are grounded in real scientific theories that could revolutionize our understanding of space travel. If humanity is ever to achieve faster-than-light travel or create stable wormholes, exotic matter and negative energy might just be the missing pieces of the puzzle. Exotic matter is a hypothetical substance that defies the rules of ordinary matter. Unlike the matter we're familiar with, which has positive mass and energy, exotic matter possesses negative mass and energy. This means it would behave in ways that seem impossible by our everyday standards. For example, instead of being attracted by gravity, exotic matter would repel it. This bizarre property is what makes it so intriguing for space travel. One of the most exciting applications of exotic matter is its potential to stabilize wormholes. Wormholes, as we've discussed earlier, are theoretical tunnels through spacetime that could connect distant parts of the universe. However, these tunnels are incredibly unstable and would collapse almost instantly under normal conditions. Exotic matter, with its negative energy, could theoretically counteract this instability, holding the wormhole open long enough for a spacecraft to pass through. Similarly, exotic matter plays a crucial role in the concept of warp drives, like the Alcubierre drive we explored earlier. A warp drive works by bending spacetime around a spacecraft, creating a bubble that allows the ship to travel faster than light without actually moving through space. But to create this bubble, you'd need a form of energy that warps spacetime in the opposite way gravity does, and that's where negative energy comes in. Exotic matter could provide the negative energy required to make this warp bubble possible. However, the challenges of discovering or synthesizing exotic matter are immense. For one, we have no direct evidence that it even exists, while some theories, like quantum field theory, suggest that negative energy could exist in tiny amounts. Creating or collecting enough of it to power a warp drive or stabilize a wormhole is far beyond our current capabilities. Even if we could produce it, the energy requirements would be astronomical and the technological hurdles would be staggering. There's also the question of whether exotic matter is stable or safe. If it behaves in such unpredictable ways, could we even control it? And what would happen if something went wrong? These are questions that scientists are still grappling with, and they highlight just how much we still have to learn about the fundamental nature of the universe. Despite these challenges, the potential of exotic matter and negative energy is too tantalizing to ignore. They represent a glimpse into a future where the boundaries of space and time are no longer limits but gateways. While we may be far from harnessing these materials, the very idea pushes the boundaries of what we believe is possible, inspiring us to dream bigger and explore further. As we continue to unravel the mysteries of the cosmos, let's turn our attention to another fascinating concept: galactic superhighways. Could there be natural pathways in space that make intergalactic travel easier than we think? Let's explore that next. Now, let's shift our gaze to a concept that might just redefine how we think about traversing the cosmos: galactic superhighways. Imagine if the universe had its own network of cosmic roads, invisible pathways carved by the very fabric of spacetime itself. These superhighways, shaped by the gravitational forces of massive objects like stars, black holes, and even entire galaxies, could offer a faster and more efficient way to travel between distant corners of the universe. At the heart of this idea is the way gravity influences the movement of objects in space. Just as rivers flow along the path of least resistance, these galactic superhighways would be shaped by the gravitational pull of massive celestial bodies. Think of it like a cosmic version of a highway system, where the gravitational fields of stars and galaxies create natural routes that spacecraft could follow, potentially reducing travel time significantly. One of the most intriguing aspects of these superhighways is how they might connect different regions of the universe. For example, the gravitational interactions between galaxies could create pathways that link them together, almost like a web of interconnected roads. If we could map these routes, it might be possible to navigate through space more efficiently, avoiding the need for constant propulsion and saving vast amounts of energy. But how would we find these superhighways? Scientists have already begun exploring this idea by studying the gravitational dynamics of our own galaxy, the Milky Way. By analyzing the movements of stars and other celestial objects, they've identified regions where gravitational forces seem to create natural pathways. These findings suggest that similar superhighways could exist on a much larger scale, connecting galaxies across the universe. Of course, there are challenges to consider. Mapping these superhighways would require an unprecedented level of precision and understanding of gravitational forces. We'd also need advanced technology to navigate these routes safely, as the gravitational fields could be both a blessing and a hazard. Too close to a black hole, for instance, and a spacecraft could be pulled in, never to escape. But with careful planning and innovation, these superhighways could become the intergalactic equivalent of a well-traveled road. What's truly exciting about this concept is how it ties into our broader understanding of the universe. Galactic superhighways remind us that the cosmos is not just a vast, empty void, but a dynamic, interconnected system shaped by the forces of gravity. They offer a glimpse into a future where humanity might not just explore the stars but navigate the universe with the same ease we navigate our own planet. As we ponder the possibilities of these cosmic pathways, let's turn our attention to another groundbreaking idea: nanotechnology in spacecraft. How could tiny machines revolutionize the way we build and maintain the vessels that carry us across the stars? That's where we're headed next. Now, let's zoom in on a concept that might seem like science fiction but is steadily becoming a reality: nanotechnology in spacecraft. Picture this: tiny machines, so small they're invisible to the naked eye, working together to build, maintain, and even repair spacecraft as they journey through the cosmos. This isn't just a futuristic dream, it's a field of science that could completely transform how we design and operate the vessels that carry us across the stars. At its core, nanotechnology involves manipulating matter at the atomic and molecular level. When applied to spacecraft, this could mean creating materials that are not only lighter and stronger, but also capable of adapting to the harsh conditions of space. Imagine a spacecraft hull that can detect damage and repair itself, or solar panels that can adjust their efficiency based on the intensity of starlight. These advancements could make long-duration space travel not just possible but sustainable. One of the most exciting possibilities is the development of self-healing materials. During a journey that could span decades or even centuries, a spacecraft would inevitably face wear and tear from micrometeoroids, radiation, and extreme temperatures. Nanotechnology could allow the ship's structure to detect cracks or breaches and automatically seal them, much like how our skin heals after a cut. This would reduce the need for external repairs and ensure the vessel remains functional throughout its mission. But the benefits don't stop there. Nanotechnology could also revolutionize how we power spacecraft. Tiny, highly efficient energy systems could be embedded directly into the ship's structure, reducing the need for bulky fuel tanks or external power sources. This would make spacecraft lighter, faster, and more agile, allowing them to travel greater distances with less energy. Additionally, nanoscale sensors could monitor every aspect of the ship's performance, from temperature to structural integrity, providing real-time data to ensure everything is running smoothly. Another groundbreaking application is in propulsion. Nanotechnology could enable the creation of ultra-efficient engines that use minimal fuel while generating maximum thrust. These engines could be powered by advanced nanomaterials that react with space's natural resources, such as hydrogen atoms scattered throughout the cosmos. This would allow spacecraft to refuel on the go, eliminating the need to carry massive amounts of fuel from Earth. Of course, there are challenges to overcome. Developing and integrating nanotechnology into spacecraft requires a deep understanding of both materials science and space engineering. We'd also need to ensure these tiny machines can operate reliably in the extreme conditions of space, where radiation and temperature fluctuations could disrupt their functionality. But with ongoing advancements in the field, these hurdles are becoming increasingly surmountable. What makes nanotechnology so compelling is its potential to make spacecraft not just tools for exploration but living, evolving systems. They could adapt to their environment, repair themselves, and even improve over time, much like biological organisms. This could pave the way for a new era of space travel, where our vessels are as resilient and dynamic as the explorers they carry. As we marvel at the possibilities of nanotechnology, let's turn our attention to another fascinating idea: parallel universes as destinations. Could intergalactic travel involve stepping into alternate realities? That's where we're headed next. Now, let's venture into a concept that stretches the boundaries of our imagination: parallel universes as destinations for intergalactic travel. What if the key to exploring distant galaxies lies not just in traversing the vastness of space, but in stepping into alternate realities? This idea, rooted in some interpretations of quantum mechanics, suggests that our universe might be just one of many, each with its own unique set of physical laws and possibilities. The concept of parallel universes, or the multiverse, proposes that countless other universes exist alongside our own, each branching off from different outcomes of quantum events. Imagine a reality where every decision you've ever made played out differently, or where the fundamental constants of physics are entirely unlike those in our universe. These alternate realities could be as close as a quantum leap away, hidden in dimensions we've yet to fully understand. But how could this relate to intergalactic travel? One intriguing possibility is that these parallel universes might offer shortcuts or pathways that bypass the immense distances of our own universe. For instance, if two universes overlap or intersect at certain points, it might be possible to hop from one to another, effectively sidestepping the need to travel through conventional space. This could open up entirely new routes to galaxies that would otherwise be unreachable within a human lifetime. Another fascinating angle is the idea that these alternate universes might contain resources or environments that are more hospitable to human life. Imagine discovering a parallel reality where the conditions for life are far more abundant, or where the laws of physics allow for technologies we can't even conceive of in our own universe. Such discoveries could revolutionize not just space travel but our entire understanding of existence. Of course, the challenges are immense. Accessing parallel universes would require a profound understanding of quantum mechanics and the ability to manipulate spacetime on a scale we can barely imagine. We'd need technologies capable of detecting and interacting with these alternate realities, as well as methods to ensure safe passage between them. And even if we could achieve this, there's the question of what we might encounter: other civilizations, entirely new forms of matter, or even versions of ourselves. Despite these hurdles, the idea of parallel universes as destinations for intergalactic travel is a tantalizing one. It pushes the boundaries of what we consider possible and invites us to rethink our place in the cosmos. Could the future of space exploration involve not just crossing galaxies but stepping into entirely new realities? The answer might lie in the quantum fabric of the universe itself. As we ponder the mysteries of parallel universes, let's shift our focus to another groundbreaking concept: antimatter propulsion. Could this be the key to unlocking the speed and efficiency needed for intergalactic travel? That's where we're headed next. Now, let's turn our attention to a concept that sounds like it's straight out of science fiction, but is grounded in real science: antimatter propulsion. Imagine a fuel source so powerful that just a tiny amount could propel a spacecraft to speeds unimaginable with today's technology. That's the promise of antimatter, a substance that, when it comes into contact with regular matter, releases energy on a scale that dwarfs even nuclear reactions. Antimatter is essentially the mirror image of ordinary matter. Every particle of matter, like an electron or a proton, has an antimatter counterpart with the opposite charge. When matter and antimatter meet, they annihilate each other, converting their entire mass into energy. This process is incredibly efficient, releasing energy millions of times greater than chemical reactions like burning rocket fuel. In fact, just 1 gram of antimatter could produce as much energy as the explosion of tens of thousands of tons of TNT. The potential for antimatter propulsion in intergalactic travel is staggering. With such immense energy density, a spacecraft powered by antimatter could theoretically reach a significant fraction of the speed of light, making journeys to distant galaxies feasible within a human lifetime. Imagine cutting the travel time to the Andromeda Galaxy from millions of years to just a few decades. The implications for exploration and colonization are mind-boggling. But here's the catch: producing and storing antimatter is one of the greatest challenges in modern physics. Antimatter doesn't exist naturally in large quantities in our universe, so we'd have to create it artificially. Current methods, like using particle accelerators, are incredibly inefficient and expensive. Producing even a single gram of antimatter would require more energy and resources than humanity currently has at its disposal. And once created, storing antimatter is no small feat. It must be kept in a vacuum and suspended in magnetic fields to prevent it from coming into contact with matter, which would cause instant annihilation. There's also the question of safety. Antimatter is so volatile that even a tiny leak could result in catastrophic explosions. Designing a spacecraft that can safely contain and utilize antimatter would require breakthroughs in materials science and engineering that we're only beginning to imagine. Despite these challenges, the allure of antimatter propulsion is undeniable. It represents a potential leap forward in our ability to explore the cosmos, offering a glimpse of a future where the stars are within our reach. As we continue to push the boundaries of science and technology, antimatter could one day become the key to unlocking the vast distances of the universe. With this in mind, let's explore another fascinating idea: cosmic strings as pathways for rapid intergalactic travel. Could these hypothetical structures in spacetime provide a shortcut through the cosmos? That's where we're headed next. Now, let's venture into a concept that stretches the boundaries of our imagination: cosmic strings. These hypothetical structures, often described as one-dimensional defects in spacetime, could offer a revolutionary way to traverse the vast distances between galaxies. Picture them as cosmic threads woven into the fabric of the universe, potentially serving as shortcuts through the cosmos. Cosmic strings are thought to be remnants from the early universe, formed during a phase transition when the universe was still cooling and expanding. These ultra-thin, incredibly dense filaments of energy could stretch across unimaginable distances, possibly even spanning entire galaxies. If they exist, they might possess extraordinary properties such as immense gravitational pull and the ability to warp spacetime around them. This makes them a tantalizing possibility for intergalactic travel. The idea is that a spacecraft could theoretically ride along a cosmic string, using its gravitational effects to achieve speeds far beyond what conventional propulsion systems could offer. Think of it like surfing a wave, but instead of water, you're riding a ripple in the very fabric of reality. This could drastically reduce the time it takes to travel between galaxies, turning what would normally be a journey of millions of years into something far more manageable. However, there's a catch. Cosmic strings are purely theoretical at this point. While they are predicted by some models of the universe, we have yet to detect any direct evidence of their existence. Even if they do exist, harnessing them for travel would require technology far beyond our current capabilities. We'd need to develop methods to locate these strings, navigate their immense gravitational forces, and ensure the safety of any spacecraft attempting to use them. Another challenge is the potential instability of cosmic strings. If they are as dense and powerful as theories suggest, they could pose significant risks to anything that comes too close. A miscalculation could result in a spacecraft being torn apart by the intense gravitational forces or flung off course into the void of space. Despite these hurdles, the concept of cosmic strings as pathways for intergalactic travel is undeniably fascinating. It opens up a realm of possibilities for exploring the universe in ways we can barely comprehend. If we could one day harness these cosmic threads, they might just become the interstellar highways of the future, connecting distant galaxies and bringing the stars within our reach. As we ponder the potential of cosmic strings, let's shift our focus to another intriguing idea: the holographic universe and how it might influence our understanding of intergalactic travel. Could the universe itself be a projection? And if so, what does that mean for our journey through it? That's where we're headed next. Now, let's dive into a theory that challenges everything we think we know about reality itself: the holographic universe. Imagine for a moment that the universe we see around us, the stars, galaxies, and even the vast emptiness of space, isn't what it appears to be. What if it's all a projection, a kind of cosmic hologram? This idea, known as the holographic principle, suggests that the three-dimensional universe we experience might actually be encoded on a two-dimensional surface, like a giant cosmic movie screen. The holographic principle stems from some of the most cutting-edge theories in physics, including quantum mechanics and black hole thermodynamics. It proposes that all the information about the universe, every star, planet, and particle, could be stored on a boundary, much like how a hologram encodes a three-dimensional image on a flat surface. If this is true, it would mean that our perception of reality is just a kind of illusion, a projection from a deeper, more fundamental layer of existence. So, how does this mind-bending idea connect to intergalactic travel? If the universe is a hologram, then the distances between galaxies might not be as fixed or insurmountable as they seem. In a holographic universe, space and time could be more malleable, opening up the possibility of manipulating the very fabric of reality to traverse vast cosmic distances. Imagine being able to rewrite the hologram, creating shortcuts or pathways that bypass the limitations of conventional space travel. One intriguing implication is that the holographic principle could redefine our understanding of energy and matter. If everything is encoded on a two-dimensional surface, then the energy required to travel between galaxies might be far less than we currently assume. This could lead to entirely new propulsion technologies, ones that don't rely on brute force but instead on manipulating the underlying code of the universe. Of course, this is all highly speculative. The holographic principle is still a theoretical framework, and we're far from proving its validity, let alone harnessing it for travel. But the idea itself is a powerful reminder of how much we still have to learn about the cosmos. It challenges us to think beyond the limits of our current understanding and imagine a future where the rules of reality might be rewritten. As we ponder the holographic universe, we're reminded that the journey to the stars isn't just about building faster ships or finding new energy sources. It's also about reimagining the very nature of space, time, and existence itself. And with that, let's turn our attention to another fascinating possibility: biological adaptation for space. What if the key to intergalactic travel lies not in our technology, but in ourselves? That's where we're headed next. Now, let's shift our gaze from the cosmic mysteries of the holographic universe to something much closer to home: ourselves. What if the key to unlocking intergalactic travel isn't just about building better ships or discovering new energy sources, but about transforming the very beings who will undertake these journeys? This brings us to Theory 20, biological adaptation for space. Imagine a future where humans are no longer limited by the frailties of our current biology. Long-duration space travel, especially across galaxies, poses immense challenges to the human body. From the effects of zero gravity on our muscles and bones to the dangers of cosmic radiation, our bodies simply aren't built for the rigors of intergalactic exploration. But what if we could change that? What if we could redesign ourselves to thrive in the harsh environments of space? One possibility is genetic modification. Scientists are already exploring ways to edit human DNA to enhance resilience, repair damage, and even extend lifespans. In the context of space travel, this could mean engineering humans with stronger bones, radiation-resistant cells, and more efficient metabolisms. Imagine astronauts who don't suffer from muscle atrophy in zero gravity, or whose bodies can repair DNA damage caused by cosmic rays. Genetic modification could make intergalactic travel not just possible but sustainable for generations. But why stop at modifying humans? Another fascinating idea is the creation of entirely new species, beings specifically designed for life in space. These organisms could be engineered to survive in extreme environments, from the vacuum of space to the toxic atmospheres of alien worlds. They might not even resemble humans at all, but instead take forms optimized for interstellar travel, such as creatures with exoskeletons, photosynthetic skin, or the ability to hibernate for centuries. These new species could act as pioneers, exploring and terraforming distant worlds before humans ever set foot on them. Of course, this raises profound ethical questions. Should we alter the human genome to such an extent? What rights would these new species have, and how do we ensure that such advancements are used responsibly? These are questions we'll need to grapple with as we move closer to making intergalactic travel a reality. Biological adaptation also opens up the possibility of merging biology with technology. Imagine humans enhanced with cybernetic implants that allow us to interface directly with spacecraft, monitor our health in real time, or even communicate telepathically across vast distances. This fusion of biology and technology could create a new kind of traveler, one perfectly suited for the challenges of intergalactic exploration. As we consider these possibilities, it's clear that the future of space travel might not just be about reaching new galaxies, but about becoming something new ourselves. The journey to the stars could be as much about evolution as it is about exploration. And with that, let's turn our attention to another cosmic force that could shape the future of intergalactic travel: dark energy and the expansion of the universe. What role might this mysterious force play in our quest to explore the cosmos? That's where we're headed next. Now, let's venture into one of the most enigmatic forces in the cosmos: dark energy. This mysterious phenomenon, which makes up about 68% of the universe, is the driving force behind the accelerating expansion of the universe. But what does this mean for intergalactic travel? Could we one day harness or even understand dark energy to propel ourselves across the vast distances between galaxies? To grasp the potential of dark energy, we first need to understand its role in the universe. Discovered in the late 1990s, dark energy is the reason galaxies are moving away from each other at an ever-increasing rate. Unlike gravity, which pulls objects together, dark energy acts as a kind of anti-gravity, pushing the fabric of spacetime apart. This expansion isn't just happening on a cosmic scale, it's happening everywhere all the time. But here's the catch, we still don't know what dark energy actually is. Is it a property of space itself, a new kind of field, or something entirely beyond our current understanding of physics? One intriguing possibility is that dark energy could be harnessed as a source of propulsion. Imagine a spacecraft equipped with technology that manipulates dark energy, using its repulsive force to create a kind of cosmic push that propels the ship forward. This could potentially allow us to travel at speeds far beyond what conventional propulsion systems can achieve, making intergalactic journeys feasible within a human lifetime. However, the challenges are immense. We'd need to develop a way to control and direct dark energy, something that currently exists only in the realm of theoretical physics. Another angle is understanding how dark energy shapes the universe's structure. As the universe expands, the distances between galaxies grow larger. This means that, over time, the journey to another galaxy becomes even more daunting. But what if we could use dark energy to our advantage? Some theories suggest that dark energy might create cosmic highways, regions of spacetime where expansion is more pronounced, effectively creating shortcuts through the universe. If we could map and navigate these pathways, we might be able to reduce travel time significantly. Of course, all of this hinges on our ability to unlock the secrets of dark energy. Right now, it remains one of the greatest mysteries in science, but as we continue to study it, we may uncover clues that not only explain the nature of the universe, but also open up new possibilities for exploration. Could dark energy be the key to unlocking intergalactic travel? Only time and a lot of scientific breakthroughs will tell. With that, let's turn our attention to another bold idea: intergalactic railguns. Could these massive devices launch spacecraft at incredible speeds, slingshotting them across the cosmos? That's where we're headed next. Now, let's shift gears to a concept that sounds like it's straight out of a science fiction blockbuster: intergalactic railguns. Imagine a device so powerful it could launch a spacecraft at speeds that make today's rockets look like they're standing still. This is the idea behind using railguns for intergalactic travel. And while it might seem far-fetched, the physics behind it is grounded in real science. A railgun works by using electromagnetic forces to accelerate a projectile to extremely high velocities. In this case, the projectile would be a spacecraft designed to withstand the immense forces involved. The idea is to build a massive railgun, possibly on the moon or another celestial body with low gravity, to launch the spacecraft into space. Once launched, the craft would continue its journey at incredible speeds, potentially reaching a significant fraction of the speed of light. This could drastically reduce the time it takes to travel between galaxies, turning what would otherwise be a journey of millions of years into something more manageable. But how feasible is this? For starters, the engineering challenges are enormous. Building a railgun capable of launching a spacecraft at such speeds would require materials and technologies far beyond what we currently have. The spacecraft itself would need to be incredibly durable to survive the intense acceleration and the harsh conditions of space. And then there's the issue of energy. Launching a spacecraft at these speeds would require an immense amount of power, likely more than we can currently generate. Another consideration is the destination. Even if we could launch a spacecraft at near light speeds, we'd still need to slow it down once it reaches its target galaxy. This would require some form of advanced braking system, adding another layer of complexity to the mission. And let's not forget the human factor. How would astronauts survive such a journey? Would they be in some form of suspended animation? Or would the spacecraft need to be a self-sustaining habitat capable of supporting life for the duration of the trip? Despite these challenges, the concept of intergalactic railguns is an exciting one. It pushes the boundaries of what we think is possible and forces us to think creatively about the future of space travel. While it may be decades or even centuries before we see anything like this become a reality, the idea itself is a testament to human ingenuity and our relentless drive to explore the unknown. With that, let's move on to another fascinating idea: the possibility of transferring human consciousness into machines or synthetic bodies, eliminating the need for biological survival during long space voyages. That's where we're headed next. Now, let's venture into a concept that blurs the line between science and philosophy: consciousness transfer. What if, instead of sending fragile human bodies across the vast emptiness of space, we could simply upload our minds into machines or synthetic bodies? This idea, often seen in science fiction, suggests a future where the essence of who we are, our thoughts, memories, and personalities, could be transferred into a durable, artificial form, capable of enduring the rigors of intergalactic travel. At its core, consciousness transfer revolves around the idea of digitizing the human mind. Scientists and futurists have long speculated about the possibility of mapping the brain's intricate network of neurons and synapses, essentially creating a digital replica of a person's consciousness. This uploaded mind could then be housed in a robotic body or even exist purely as data within a computer system. For intergalactic travel, this would eliminate many of the challenges associated with biological survival, such as the need for food, water, oxygen, and protection from radiation. But how close are we to making this a reality? The truth is, we're still in the very early stages of understanding the human brain. While we've made strides in neuroscience, mapping the entire brain with enough detail to replicate consciousness remains a monumental task. Even if we could achieve this, the ethical implications are profound. Would a digital copy of your mind truly be you, or just a simulation? And what happens to the original biological version of you? These questions touch on the very nature of identity and existence, making consciousness transfer as much a philosophical debate as a scientific one. From a practical standpoint, transferring consciousness into machines could revolutionize space exploration. Synthetic bodies could be designed to withstand extreme conditions, from the vacuum of space to the crushing gravity of alien worlds. They wouldn't age, get sick, or require sleep, making them ideal for missions that span centuries or even millennia. Additionally, these artificial forms could be upgraded or repaired, ensuring they remain functional for the duration of the journey. However, the challenges are immense. Beyond the technical hurdles of brain mapping and data storage, there's the question of how to power and maintain these synthetic bodies over such vast distances. And let's not forget the psychological impact. Would a machine-based consciousness retain the same emotions, creativity, and sense of purpose that define us as humans? Or would it become something entirely different? Despite these uncertainties, the concept of consciousness transfer opens up thrilling possibilities for the future of intergalactic travel. It challenges us to rethink what it means to be human and pushes the boundaries of our understanding of life itself. While it may remain in the realm of speculation for now, it's a fascinating glimpse into how we might one day transcend the limitations of our biological forms. With that, let's turn our attention to another intriguing possibility: how the eventual collision of the Milky Way with the Andromeda Galaxy might create unexpected opportunities for intergalactic travel. That's where we're headed next. Now, let's shift our gaze to a cosmic event so monumental that it could reshape the very fabric of our galaxy: the collision of the Milky Way with Andromeda. While this might sound like the plot of a science fiction movie, it's a real event predicted to occur in about 4.5 billion years. But what does this mean for the future of intergalactic travel? Surprisingly, such a collision might not spell destruction. It could open up entirely new possibilities for exploration. When two galaxies collide, they don't crash in the way we might imagine. Instead, their stars and planets pass through each other like two clouds merging in the sky. This is because the vast distances between celestial objects mean that direct collisions are incredibly rare. What happens, though, is a dramatic reshaping of the galaxy's structures. Gravity pulls and twists them, creating new pathways and altering the distribution of stars, planets, and even dark matter. For intergalactic travelers, this cosmic dance could provide unexpected opportunities. One of the most intriguing possibilities is the creation of gravitational highways. As the Milky Way and Andromeda interact, their combined gravitational forces could form natural pathways that make it easier to travel between stars and even between galaxies. These pathways might allow spacecraft to harness gravity in ways that reduce the energy needed for propulsion, potentially making intergalactic travel more feasible. Imagine a future where we use these galactic superhighways to navigate the cosmos, much like ancient explorers used trade winds to cross oceans. Another potential benefit of this collision is the increased likelihood of star formation. When galaxies collide, the shockwaves and gravitational interactions can trigger the birth of new stars and planetary systems. For intergalactic travelers, this means more destinations to explore and potentially more resources to sustain long journeys. These new star systems could serve as stepping stones, allowing us to venture further into the universe than ever before. Of course, such a collision also comes with challenges. The chaotic environment of merging galaxies could pose risks to spacecraft, from increased radiation to unpredictable gravitational forces. But for a civilization advanced enough to harness the opportunities, these challenges might be outweighed by the potential rewards. The collision of the Milky Way and Andromeda could mark the beginning of a new era of exploration, where the boundaries between galaxies become less daunting and more like bridges waiting to be crossed. As we ponder this distant future, it's worth considering how such a monumental event might inspire humanity to push the limits of what's possible. The collision of galaxies isn't just a scientific curiosity. It's a reminder that the universe is constantly evolving, offering new opportunities for those bold enough to seize them. And with that, let's turn our attention to another fascinating concept: quantum tunneling, and how it might revolutionize our ability to traverse the cosmos. Now, let's venture into the realm of the incredibly small to explore something that could have enormous implications for the future of intergalactic travel: quantum tunneling. This phenomenon, rooted in the strange and counterintuitive world of quantum mechanics, might just hold the key to traversing vast cosmic distances in the blink of an eye, though, for now, it remains firmly in the realm of theory. Quantum tunneling is a process where particles, such as electrons, can pass through barriers that, according to classical physics, should be impossible to overcome. Imagine throwing a ball at a wall. In the everyday world, the ball would simply bounce back. But in the quantum world, there's a small chance the ball could somehow appear on the other side of the wall without ever having to go over or through it. This bizarre behavior is a fundamental aspect of quantum mechanics, and it's been experimentally verified in countless ways. But what does this have to do with intergalactic travel? The idea is that if particles can tunnel through barriers, perhaps entire spacecraft, or even humans, could one day exploit this phenomenon to traverse the vast distances between galaxies. Instead of traveling through space in the traditional sense, a spacecraft might tunnel through the fabric of spacetime itself, effectively bypassing the need to cover the immense distances that separate us from other galaxies. It's a concept that sounds like science fiction, but it's grounded in real physics. One of the most exciting aspects of quantum tunneling is the possibility of instantaneous travel. If a spacecraft could tunnel from one point in the universe to another, the journey might take no time at all from the perspective of those on board. This would eliminate the need for generation ships, cryogenic freezing, or even warp drives, as the travelers could arrive at their destination in what feels like an instant. However, there's a catch, or rather, several catches. First, quantum tunneling is typically observed on the scale of subatomic particles. Scaling it up to the size of a spacecraft, or even a single human, would require overcoming monumental technological and scientific hurdles. Second, the probability of tunneling decreases exponentially with the size and complexity of the object involved. While an electron might tunnel through a barrier relatively easily, the chances of a spacecraft doing the same are currently beyond our understanding. And third, even if we could harness quantum tunneling for travel, controlling the destination would be a significant challenge. Without precise control, a spacecraft might end up anywhere or nowhere in the universe. Despite these challenges, the concept of quantum tunneling as a method of intergalactic travel is a tantalizing one. It pushes the boundaries of our understanding of physics and forces us to think creatively about the possibilities of the cosmos. While it may remain theoretical for now, it's a reminder that the universe is full of mysteries waiting to be unlocked, and that the future of exploration might be far stranger than we can imagine. As we ponder the potential of quantum tunneling, let's turn our attention to another fascinating idea: the concept of space-time foam and how it might contain micro-wormholes that could revolutionize our ability to traverse the cosmos. Now let's dive into a concept that sounds like it's straight out of a science fiction novel, but is deeply rooted in the cutting-edge theories of modern physics: space-time foam. This idea takes us into the bizarre and unpredictable world of quantum mechanics, where the very fabric of spacetime itself is far from smooth and continuous. Instead, it's thought to be a frothy, turbulent sea of fluctuations at the tiniest scales imaginable, a phenomenon known as space-time foam. At the quantum level, space-time isn't the calm, unchanging backdrop we often imagine. Instead, it's constantly bubbling and churning, with tiny fluctuations creating a chaotic, foam-like structure. These fluctuations are so small that they occur on scales trillions of times smaller than an atom, making them impossible to observe directly with current technology. But according to theoretical physics, this foam is where the rules of the universe as we know them begin to break down, and where some of the most extraordinary possibilities for intergalactic travel might lie. One of the most intriguing ideas tied to space-time foam is the existence of micro-wormholes. These hypothetical tunnels through space-time could, in theory, connect distant points in the universe, allowing for rapid travel between them. Unlike the larger wormholes often depicted in science fiction, micro-wormholes would be incredibly tiny, far too small for a spacecraft or even a single atom to pass through. But here's where things get fascinating. If we could somehow harness or stabilize these micro-wormholes, they might offer a way to traverse vast cosmic distances in an instant. The concept hinges on the idea that space-time foam isn't just a chaotic mess but a network of potential pathways. These micro-wormholes could act as shortcuts through the fabric of space-time, bypassing the need to travel through the vast emptiness of space. Imagine being able to step through a doorway that takes you from one galaxy to another in the blink of an eye. It's a mind-bending idea, but one that's grounded in the mathematics of quantum gravity and general relativity. However, as with many of the theories we've explored, there are significant challenges to overcome. First, micro-wormholes are incredibly unstable. They would likely form and collapse in an instant, making them useless for travel unless we could find a way to keep them open. Second, even if we could stabilize them, navigating through such a chaotic and unpredictable environment would be a monumental task. The space-time foam is a realm where the laws of physics as we know them may no longer apply, meaning we'd need entirely new tools and theories to make sense of it. Despite these hurdles, the idea of space-time foam and micro-wormholes is a thrilling one. It challenges us to rethink our understanding of the universe and pushes the boundaries of what might be possible. While it remains firmly in the realm of theory for now, it's a reminder that the cosmos is full of surprises, and that the future of intergalactic travel might be far stranger and more wondrous than we can currently imagine. As we wrap up this exploration of space-time foam, let's turn our attention to another fascinating concept: cosmic inflation and the possibility of bubble universes, which could open up entirely new avenues for intergalactic exploration. Now let's shift our gaze to a theory that takes us even further into the realms of the unimaginable, cosmic inflation and the possibility of bubble universes. This concept builds on the idea that our universe is just one of many, floating in a vast cosmic ocean of other universes, each with its own unique properties and laws of physics. It's a mind-expanding idea that could redefine not only how we see the cosmos, but also how we might one day explore it. Cosmic inflation is a theory that explains the rapid expansion of the universe in the moments following the Big Bang. According to this idea, the universe didn't just expand, it exploded outward at an incomprehensible speed, stretching spacetime itself. But here's where it gets even more intriguing. Some versions of this theory suggest that this rapid expansion didn't stop everywhere at the same time. Instead, certain regions of spacetime continued to inflate, creating bubbles that eventually became their own separate universes. These bubble universes could exist alongside ours, each with its own distinct physical constants, dimensions, and even realities. Imagine a cosmic foam where each bubble represents a universe, and the space between them is a vast, ever-expanding void. This multiverse scenario raises the tantalizing possibility that intergalactic travel might not be limited to our own universe. If we could find a way to traverse the boundaries between these bubble universes, we might unlock entirely new realms of exploration. But how could such a journey even be possible? One possibility lies in the nature of spacetime itself. If bubble universes are connected by regions of spacetime that are still inflating, it's conceivable that these regions could act as bridges or gateways. Traveling through these bridges would require technologies and understanding far beyond our current capabilities, but the idea is rooted in the mathematics of cosmic inflation. Another fascinating angle is the role of quantum fluctuations. Just as space-time foam creates micro-wormholes, quantum effects might create temporary pathways between bubble universes, offering fleeting opportunities for travel. Of course, the challenges are immense. For one, we have no way of detecting or observing these bubble universes directly. They exist beyond the observable horizon of our own universe, making them inaccessible with current technology. Even if we could find a way to reach them, the physical laws governing these universes might be completely alien to us. What if gravity works differently there? What if time flows backward? The possibilities are as thrilling as they are daunting. Yet, the idea of bubble universes and cosmic inflation pushes us to think bigger. It challenges us to consider that our universe might be just one small part of a much grander cosmic tapestry. And while the practicalities of traveling between these universes remain firmly in the realm of speculation, the theory itself opens up a universe of possibilities, literally. As we ponder the implications of bubble universes, let's turn our attention to another extraordinary idea: gravitational wave surfing, a concept that could revolutionize how we think about propulsion and intergalactic travel. Now let's dive into a concept that feels like it's straight out of science fiction, but is deeply rooted in the science of spacetime itself: gravitational wave surfing. Imagine harnessing the ripples in the fabric of the universe to propel spacecraft across galaxies. It's an idea that could redefine how we think about propulsion and intergalactic travel. Gravitational waves are ripples in space-time, first predicted by Albert Einstein over a century ago. These waves are created by some of the most violent and energetic events in the universe, like the collision of black holes or the explosion of massive stars. When these events occur, they send shockwaves through spacetime itself, much like a stone creates ripples when dropped into a pond. These ripples travel across the cosmos at the speed of light, carrying with them immense energy. The idea of gravitational wave surfing is to use these ripples as a kind of cosmic surfboard. A spacecraft equipped with the right technology could theoretically ride these waves, using their energy to accelerate to incredible speeds. Unlike traditional propulsion methods which rely on fuel or external forces, This approach would tap into the natural movements of spacetime itself. It's a bit like catching a wave in the ocean, but on a cosmic scale. One of the most exciting aspects of this theory is that gravitational waves are not bound by the same limitations as light or matter. They can pass through anything: stars, planets, even entire galaxies without losing energy. This means a spacecraft riding gravitational waves could potentially travel vast distances without being slowed down by obstacles in its path. It's a concept that could make intergalactic travel not just possible but efficient. But how would this work in practice? The first challenge would be detecting and predicting gravitational waves with enough precision to plot a course. While we've made incredible strides in detecting these waves with observatories like LIGO and Virgo, using them for propulsion would require a level of accuracy and control that's far beyond our current capabilities. Another hurdle is the sheer scale of the energy involved. Gravitational waves are incredibly powerful, but they're also incredibly subtle. Harnessing them would require technology that can amplify and direct their energy in a controlled way. Despite these challenges, the potential is staggering. Gravitational wave surfing could allow us to travel across galaxies in a fraction of the time it would take using conventional methods. It could open up new frontiers of exploration, allowing us to reach distant star systems and even other galaxies within a human lifetime. And because gravitational waves are a natural phenomenon, this method of travel would be sustainable, relying on the universe's own energy rather than finite resources. As we explore the possibilities of gravitational wave surfing, it's clear that this theory pushes the boundaries of what we thought was possible. It challenges us to think beyond traditional propulsion and consider the universe itself as a tool for exploration. While the practicalities remain speculative, the idea is a testament to human ingenuity and our relentless drive to explore the cosmos. With this mind-bending concept in mind, let's turn our attention to another groundbreaking idea: the concept of an intergalactic internet, a network that could unite civilizations across galaxies. Now, shifting our gaze to the stars and beyond, let's explore a concept that could revolutionize how civilizations communicate across the vast expanse of the cosmos: the intergalactic internet. Imagine a network so vast and advanced that it connects not just planets within a single galaxy, but entire galaxies themselves. This idea isn't just about faster communication. It's about creating a universal framework for sharing knowledge, culture, and ideas on a scale we can barely comprehend. At its core, the intergalactic internet would function as a cosmic web, linking civilizations separated by millions or even billions of light years. Unlike our current internet, which relies on cables, satellites, and radio waves, this network would need to overcome the immense distances and time delays inherent in space. One proposed solution is the use of quantum entanglement, a phenomenon where particles become interconnected regardless of distance. If harnessed, this could allow for instantaneous communication across galaxies, bypassing the limitations of traditional signals that travel at the speed of light. But building such a network would require more than just advanced physics. It would demand a level of technological sophistication far beyond what we currently possess. For instance, we'd need to develop devices capable of creating and maintaining entangled particles over astronomical distances. We'd also need to establish relay stations, perhaps powered by self-replicating probes, to ensure the network remains stable and accessible across the vast reaches of space. These stations could act as cosmic routers, directing information flows between galaxies and ensuring no civilization is left isolated. The implications of an intergalactic internet are profound. It could enable the exchange of scientific discoveries, artistic creations, and even philosophical ideas between civilizations that might never meet in person. Imagine a galaxy sharing its knowledge of advanced energy sources with another struggling to power its cities, or a distant civilization sending its music and stories across the void to inspire others. This network wouldn't just be a tool for communication, it would be a bridge between cultures, fostering collaboration and understanding on a universal scale. Of course, challenges abound. The sheer scale of such a project is staggering, requiring resources and coordination that might take millennia to achieve. There's also the question of compatibility. How do you create a universal language or protocol that every civilization can understand and use? And what about security? An intergalactic internet would need safeguards to prevent misuse or interference, ensuring that the network remains a force for good rather than conflict. Despite these hurdles, the vision of an intergalactic internet is a testament to humanity's enduring desire to connect and explore. It challenges us to think beyond the boundaries of our own galaxy and imagine a future where the universe is not just a place to visit, but a community to belong to. As we continue to push the limits of technology and imagination, the idea of a cosmic network uniting civilizations across galaxies reminds us that the universe is not just a collection of stars and planets, it's a shared home waiting to be connected. With this vision of a connected cosmos in mind, let's turn to our final theory, one that ties together many of the ideas we've explored, the Fermi paradox and its implications for intergalactic travel. Now, as we approach the final frontier of our exploration, let's delve into a theory that ties together many of the ideas we've discussed, the Fermi paradox and its connection to intergalactic travel. The Fermi paradox is one of the most intriguing questions in science. If the universe is so vast and filled with potentially habitable planets, why haven't we encountered any signs of extraterrestrial civilizations? This paradox raises profound questions about the nature of life, intelligence, and the challenges of traversing the cosmos. At its heart, the Fermi paradox challenges our assumptions about the likelihood of intelligent life existing elsewhere in the universe. With billions of galaxies, each containing billions of stars and planets, it seems statistically improbable that Earth is the only place where life has evolved to a level capable of space travel. Yet, despite decades of searching, we've found no definitive evidence of alien civilizations. This absence of contact could suggest that intergalactic travel is far more difficult, or perhaps far less common than we imagine. One possible explanation is that the distances between galaxies are simply too vast for even the most advanced civilizations to overcome. While we've explored theories like wormholes, warp drives, and generation ships, the reality is that these technologies remain speculative. The energy requirements, timescales, and technological hurdles involved in crossing intergalactic space might be insurmountable, even for civilizations far more advanced than our own. This could mean that most civilizations are confined to their home galaxies, unable to bridge the cosmic void. Another possibility is that intelligent life is rare or short-lived. Perhaps civilizations tend to self-destruct before they develop the capability for intergalactic travel, whether through war, environmental collapse, or other existential threats. Alternatively, intelligent life might be so rare that the chances of two civilizations existing at the same time and being close enough to communicate are vanishingly small. In this scenario, the silence we observe might not be a failure of technology, but a reflection of the universe's inherent loneliness. The Fermi paradox also raises questions about how civilizations might choose to explore or communicate across galaxies. Some might prioritize survival over expansion, focusing their resources on preserving their own worlds rather than venturing into the unknown. Others might develop technologies that are completely beyond our understanding, making their presence undetectable to us. For example, a civilization that has mastered quantum communication or dimensional travel might leave no trace that we can recognize. Ultimately, the Fermi paradox reminds us that intergalactic travel is not just a technological challenge but a philosophical one. It forces us to confront the possibility that we might be alone in the universe, or that the universe is far stranger and more complex than we can imagine. As we continue to search for answers, the paradox serves as both a humbling reminder of our limitations and an inspiring call to push the boundaries of what we know. With this final theory, we've journeyed through 30 ideas that explore the possibilities and challenges of humanity's first steps into intergalactic space. From wormholes to warp drives, from cryogenic sleep to cosmic superhighways, each theory offers a glimpse into the extraordinary future that might await us among the stars. As we conclude, let's reflect on the awe-inspiring scale of the universe and the boundless potential of human ingenuity. The journey to the stars is not just about reaching new worlds, it's about discovering who we are and what we might become. As we bring our journey through these 30 theories to a close, it's impossible not to feel a sense of wonder at the sheer scale of what lies beyond our galaxy. From the tantalizing possibility of wormholes acting as cosmic shortcuts to the mind-bending concept of warp drives bending spacetime, each theory offers a unique glimpse into the future of intergalactic travel. We've explored the potential of generation ships carrying humanity across the stars, the promise of cryogenic suspension preserving travelers for millennia, and the revolutionary idea of self-replicating probes paving the way for our arrival. Each of these ideas pushes the boundaries of what we believe is possible, challenging us to think bigger and dream bolder. Yet, alongside these awe-inspiring possibilities, we've also confronted the immense challenges that stand in our way. The vast distances between galaxies, the staggering energy requirements of advanced propulsion systems, and the ethical dilemmas of long-duration space travel remind us that the journey to the stars is no small feat. Theories like black hole slingshots, quantum entanglement communication, and antimatter propulsion highlight the incredible ingenuity required to overcome these obstacles. And as we've seen with the Fermi paradox, the very nature of the universe itself might present barriers we have yet to fully understand. What ties all these theories together is a shared sense of curiosity and determination. They remind us that the pursuit of intergalactic travel is not just about reaching new worlds, it's about expanding our understanding of the cosmos and our place within it. Whether we're harnessing the power of Dyson Spheres, navigating cosmic superhighways, or exploring the mysteries of dark energy, each step forward brings us closer to answering some of the most profound questions humanity has ever asked. So, as we conclude this exploration, I want to leave you with a question. Which of these theories resonates most with you? Is it the idea of generation ships carrying humanity's legacy across the stars, or the futuristic vision of warp drives bending the fabric of spacetime? Perhaps you're drawn to the philosophical implications of the Fermi paradox or the technological marvel of self-replicating probes. Whatever your choice, I encourage you to share your thoughts in the comments below. Let's continue this conversation and imagine together what the future of intergalactic travel might hold. If you enjoyed this journey through the cosmos, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an exploration into the mysteries of the universe. Thank you for joining me on this adventure, and remember, the stars are not just our destination, but a reflection of our limitless potential. Until next time, keep looking up.